what I'd like to tell you about today is to have some fun with finite covers of three manifolds. So this is a story that will start out being purely topological, but as so often in studying three manifolds, one's led to introduce the tool of geometry, specifically hyperbolic geometry. And once that's in play, that will allow us to bring arithmetic, by which I mean number theory, into the picture. And I'd like to spend the second half of this talk will be about a conjecture which is motivated in part by some questions in number theory, but will actually sort of be topological in nature. Okay, so I'm going to be talking about today is three manifolds, just some typical closed, oriented three manifolds. So the examples you're all familiar with include things like the three-sphere or the three-dimensional torus, or maybe genus 2 surface cross a circle or lens space. And the starting point for today's talk is the geometrization theorem. This is a perspective introduced by Thurston in the late 70s, improved in generality by Perelman a little over 10 years ago. And this geometrization theorem says that we can attempt to understand the topology of such a three manifold by means of geometry. So any closed, let me stop writing oriented, three manifold has a geometric decomposition. Well, need to explain what that is, but first let me just point out in the list of sample manifolds I wrote down, right, if we view the three-sphere as the unit sphere in R4, it has a nice round metric of constant curvature. The three-dimensional torus I could view as the quotient of three-dimensional Euclidean space by the integral lattice of translations. This is going to have a nice locally homogeneous Riemannian metric, locally modeled on the geometry of constant curvature in dimension 2, H2, across the line. I guess this one is the quotient of the three-sphere by a nice cyclic group. So this is, again, an example of constant curvature. So I don't want to tell you exactly what this decomposition involves. It involves undoing connect sum. Let me just at least write a few words. So you undo connect sum, and then there's some analogous kind of decomposition along tori that you might have to cut along in some more complicated situations. And then once you're done with this cutting, you get pieces, all of which admit a locally homogeneous metric, which will come in one of 8 kinds. So it might be something of constant positive curvature or Euclidean space, Euclidean flat metric, or some kind of product thing, or the most important suitable sentence is generic, or at least key case, will be when these pieces are hyperbolic manifolds. So they admit where they emit a metric of constant curvature minus 1. And for the questions that I'm going to talk about today, this is my excuse for not telling you the details of this geometric decomposition. For the questions I want to talk about today, all the interesting cases will be in the case of hyperbolic geometry. Which is not to say it doesn't take manifolds that admit the other 7 geometries. They're sort of completely classified. They're Seifert-Fibert spaces, things like that. And when you have manifolds that are built out of pieces, especially when you're gluing along tori, I'm not saying that it's immediately obvious the properties of the manifold you get by gluing. There are subtle questions there, but in the present context, I'm just going to they're not hard in the present context. In any event, I'm going to push it under the rug. So I'd like to focus just today on these hyperbolic manifolds, and so tell you about covers of hyperbolic manifolds. You should feel free to interrupt me with questions at any time. So to start off, let's address the question, are there finite covers? Seems like I'm going to spend a whole hour talking about them. There better be some. And one corollary of the geometrization theorem is that finite covers do exist. So if we have a closed 3-manifold, which is not the 3-sphere, then M has a non-trivial finite cover and so just some covering map of finite degree. Equivalently, if you're more algebraic, want to take a more algebraic perspective, this is just saying that the fundamental group of M contains a proper subgroup of finite index. And so I'd like to explain why this is a consequence of geometrization here. Even though it seems like a purely topological or maybe algebraic question, and so the proof of the corollary, at least in the case when M is hyperbolic. So we have a hyperbolic manifold that has this metric of constant curvature -1. So if we look at its universal cover is going to be the 3-dimensional hyperbolic space. All right, so that's just an open unit ball in R3 with a funny metric, namely the metric where, well, it's conformally the same as Euclidean space. So angles in the picture look right, distances are badly distorted. And so in particular, I want to distort it by a factor, which means that stuff near the boundary, right, this is an open ball, stuff near the boundary of the open ball is much, much bigger than it appears to us. So something in the middle here, some little thin box that might seem to us have volume a tenth. If we move, this actually is homogeneous, just like Euclidean space. If we move this box out towards the boundary, then to us, it would shrink even though it retains the same volume. And so this is its universal cover, and just not sure if everybody's seen this before, but just point out some features. So if you look at the equatorial circle on this sphere, and you look at this disk, that's a copy of the 2-dimensional hyperbolic space, which sometimes you visualize like in an upper half space model, or upper half plane. So in particular, geodesics in this copy of H2, they're circles, Euclidean circles, which meet the boundary. The boundary is not part of H3, but it can be defined intrinsically. They're circles which meet the boundary at right angles. That's true not just in this copy of H2, but more generally. So here are some nice. And as I said, angles are right. So the fact that this looks like it's about 90 degrees means it is about 90 degrees. The fact that these are all finite length is highly misleading. All right, so this is its universal cover, and I want to take the perspective on my manifold as viewing it. Right, so the fundamental group of M acts on its universal cover by deck transformations. Those, of course, preserve the metric, which was pulled back from downstairs. So in particular, I can think of the 3 manifold as the quotient of hyperbolic 3 space by the action of its fundamental group. And I'm thinking now of the fundamental group as a subgroup. These are a bunch of isometries of hyperbolic 3 space. So I want to think about this as a subgroup of, as I said, isometries. Let's say all my manifolds are oriented, whether I remember to mention it or not. Orientation preserving isometries of H3. And this group is just the Lie group This is just the Lie group of 2 by 2 matrices of determinant 1, I guess modulo its center. If you think about a 2 by 2 matrix like this as corresponding to a Mobius transformation, right? So you have the sphere at infinity here. You think about that as the Riemann sphere. So given a matrix here, you get a nice Mobius transformation on this sphere at infinity, as it's called. It turns out there's a way to extend that continuously to the whole ball in a way that is actually an isometry of H3 itself. Okay, so anyway, it's one way of thinking about our hyperbolic manifold. In the same way, earlier I had the example of the 3 torus, viewing it as the quotient of Euclidean 3 space by Z cubed. Now we have our 3 manifold, hyperbolic 3 manifold, it's a quotient of hyperbolic space. So how is this relevant to the corollary? This probably just seemed like a digression. The fact that's relevant is that we've taken our group and we've embedded it as a group of matrices. And yes?
That's the first stupid question. So maybe I'm not understanding the representation. Why SL2 and not SL3 if it's an isometry all of H3?
Oh, because...
that's the complex dimension versus the...
No, it's because, right, so the reason this is 2 is the most natural way to see this as in this picture is to view an element here as giving me a Mobius transformation which is acting on the Riemann sphere on CP1. So there's no sort of, there's the action that you get here on H3 is not like a linear action at all. It's this kind of weird thing that your linear action on C2 gives you this Mobius transformation on CP1. And it turns out that that extends, not in a linear way, but it extends to this, and that gives us your thing. So the fact is that any finitely generated group of matrices in any dimension over any field has finite quotients. Where I guess implicitly I mean non-trivial group and non-trivial quotients. So in particular, given that we now have a group of matrices, we're going to get this. Given that, right, we have a nice closed 3 manifold, so it has some triangulation, so certainly its fundamental group is finitely generated. And the reason for this, I'm just going to give what will seem initially to be an example, but the simplest group of matrices I can think of, non-trivial in any way, would be, say, SL2Z, right? And if you wanted a quotient of SL2Z, well, one thing you could do is you could just reduce the entries of the matrices mod some number. Right? So you could look at the map from SL2Z to SL2Z mod NZ. And it's not so hard to see that this map is onto in this case. And so that is a non-trivial finite quotient, and so we could take the kernel and gets what we'll call a congruent subgroup. It's a particular kind of subgroup. And of course, by taking n to be a really large number, you can make this subgroup be in some sense very small, have very large index. And as I said, this seems like an example, maybe an example not particularly relevant to the three-manifold context. But in fact, the point is, if you have a finitely generated group of matrices, the entries of those matrices, of the generators, they're going to live in some extension of the rationals that's generated by finitely many things. It's not necessarily a number field, might have some transcendental part, but anyway, they're going to live in a reasonably small ring. And consequently, that ring, I really shouldn't say field, I really wanted to think of it as a ring, extension of Z. That ring will have ideals, so you'll be able to take quotients of that ring, and you'll be able to play exactly the same game. All right, so that's the proof of the corollary. Are there questions on the proof? So this is something I find pretty amazing. This is the proof I just gave is essentially the only known proof of this corollary. There are other proofs, but they still involve hyperbolic geometry and are much harder. And so the way then that you prove this, or to find, someone hands you a three-manifold, how does this proof tell you to find a finite cover? The way it works is you start with your three-manifold. You put some arbitrary Riemannian metric on it to start. And then you're supposed to find this geometric decomposition. So the way Perlman did this, right, is he starts with this generic Riemannian metric, and then he flows it under Hamilton's Ricci flow, which is, it's a parabolic PDE. It's not such a horrible thing. But things happen. Singularities will develop sometimes in finite time. Perlman's key contribution is to analyze the singularities of this flow and tell you how to move past the singularities and get on with your life. And eventually, things bubble off or whatever. But in the generic case, eventually, the metric smooths down. It becomes homogeneous. And in the infinite time limit, becomes this hyperbolic metric. And then, once you finally, after all this, it's worth about 2 Fields medals, I think, to find this hyperbolic metric, you've learned that your fundamental group lives inside some bunch of matrices, and so therefore you know something about its algebra. So other questions? So yes?
The algebraic fact, is that
So, no. It basically is just this. So this was first proved by Maltsev in 58, maybe, 1958, 68, maybe, somewhere around there. Yes.
Didn't Hempel give this proof? I don't know who's giving for the car.
Right. So Hempel proved that this follows from geometrization. Correct. So I just gave you the proof when the manifold's hyperbolic. For a general three-manifold, it's decomposition. And while each of the pieces, it's easy to see, have finite covers, to prove the whole thing has finite covers, you need to show you can do this in a way that's consistent with stitching across. And that's the work of Hempel. Yeah, so. Thank you. Okay, so all right, so I spent the first 20 minutes of my talk convincing you finite covers exist. Get to spend 40 minutes telling you something about them. So the first result I want to mention, which I'm certainly going to give short shrift to, is the work of Egal. Who a few years ago proved what had been called the virtual Hawking conjecture, which says that any closed three-manifold with infinite fundamental group has a finite cover which has some non-trivial cohomology. So it has a finite cover M tilde where, let's just say, the first cohomology of M with integral coefficients is non-zero. And of course, as you all know, it's Poincare dual to the second homology. Right? And so you can think about classes in here as being represented by sort of honest embedded surfaces. So you can interpret this theorem as saying if you have a closed three-manifold with infinite fundamental group, then it has a finite cover which contains an interesting surface. Thank you. And you can see that this hypothesis here is necessary because, of course, another way I can view this, first cohomology, as homomorphisms from the fundamental group of M tilde to Z. So another way of stating this is saying is as long as your three-manifold has infinite fundamental group, then you can find a finite index subgroup which has an epimorphism onto Z. So this uses the work of Donnie Wise on cubulating groups, and also Egel's work with Groves and Manning. I could easily spend the remaining 40 minutes, I could probably actually easily spend all of my 3 lectures telling you about that amazing work. What I'm going to do instead is talk about a conjecture which will still be, which in some sense is orthogonal to this one. So if we're thinking about the homology of our cover here, let's say the first homology, right? As you know, of course, it's got some free abelian part plus some torsion part. And of course, the free part, that just corresponds to the first cohomology. So Egel tells us that in particular, you can find a finite cover where this thing is non-trivial. And as said, I mean, this corresponds by duality to surfaces of a certain kind in your three-manifold. So this has sort of obvious geometric meaning. But the torsion part, at least the torsion which is prime to 2, doesn't have any obvious geometric meaning. Right? If I tell you I have a three-manifold and there's 121 torsion in its first homology, I mean, does this tell you anything? Does it give you a surface or some kind of concrete thing? I mean, okay, homology is a concrete thing. It means there's some cycle and so on, but it doesn't have the sort of, it's not clear how I should interpret it. It's very algebraic. And so what I'd like to tell you about today, and this will also motivate my talk tomorrow, is one interpretation of this torsion, or one much more geometric thing that it appears to encode. So what I'd like to tell you about now is a conjecture. So officially now this is a mixed media talk. So in the version I'm going to state this conjecture, it was first proposed by the number theorists Bergeron and Venkatesh, but in closely related form postulated by Feng Lei at the same time. And also ideas like this certainly go back to the work of Look. So this was proposed maybe 2 or 3 years ago. So suppose suppose we have a closed hyperbolic three-manifold. A little worried about this pen here. closed hyperbolic 3 manifold, which is, this one's not much better. It's going to be very multicolored, which is arithmetic. So this is something that came up in the last talk, but I won't precisely define this either. But a good working definition is it's the kind of hyperbolic 3 manifold that a number theorist cares about, which is why these guys were looking at them. And it's not close. Many of these hypotheses can probably be dropped. It's one of the reasons I don't want to belabor them too much, although I don't think we understand the right generality for this conjecture. So suppose we have these guys, well, all right, so here we have our manifold. And I just spent a lot of time telling you it has finite covers. And that was fun to build that finite cover. Let's do it again. And legally what's been done before can be legally done again, so another finite cover. And so we have what's called tower. And where, let's just say, this is kind of technical, you can just ignore it, where let's say that each of the covers over the base is regular, so it corresponds to a normal subgroup of the fundamental group. Let me say they're congruent, so that those kind of covers I was talking about here, they're analogs. And then finally, I want to say that in this tower, we unwind all of the topology of this manifold here. So if I have any loop in M0, eventually that loop becomes unwound if I go far enough up this tower. So I guess maybe the simplest way to say this is algebraic. So let's say that we look at the subgroups of these guys. Subgroups of pi 1 of n, these are, thank you. These are normal subgroups of finite index. Then this is, their intersection is trivial. And so no matter what loop you start with, eventually it leaves. All right, that was all hypotheses. There's supposed to be a conclusion, right? Then, this mysterious torsion. So let's look at the first homology of one of these covers. And let's just look at the torsion part. Let me drag this over just in case the podium's blocking it. So what they conjecture is that eventually this is non-trivial. And in fact, it's very non-trivial. Its size, so you can look at the size of this finite abelian group, should be huge. And it should be growing at a rate which is exponential in the volume of the manifold. And the rate of exponential growth is a uniform constant independent of anything. So to put that in a formula, if we take the size of that group, take the log of that, divide by the volume of the manifold, then this limit, A, should exist and should be equal to 1 divided by 6 pi. That's the conjecture. Well, let me rewrite this conjecture slightly, which will only make it seem more mysterious. I mean, everything in the statement here we could interpret purely algebraically if we wanted. Right? So we could, if we could do the first homology, that's just the abelianization of the fundamental group. We look at the fundamental group of Mn, so we could take its abelianization. Again, we care about the torsion part. Look at its size. Take the log. Let's see. Well, the volume of the manifold is not purely related to the. We have the volume of the manifold. If I want to rewrite this, I mean, this is equal to the volume of the base manifold times the degree of the cover. And of course, the degree of the cover is just the index of the subgroup. So this in purely terms of algebra. So if I just take the volume of M and kick it to the other side, the conclusion there could be rewritten as if you look at the abunionization of the fundamental group, torsion, size thereof, divide that by the index of the subgroup, then this is supposed to limit to the volume of the manifold, hyperbolic volume, divided by 6 pi. So it's saying that somehow you can at least approximately read off the volume of the manifold from looking at a subgroup of large index. So that's, I mean, I think this is a very striking conjecture, but I think the way I presented it to you, I've made it seem even more striking than it really is. Because one of the reasons that the whole Thurston perspective is so important in three manifolds is not just that you have these geometries, that you have this geometric decomposition, but in the generic case of hyperbolic geometry, it's unique. So Mostow rigidity says that in the hyperbolic manifold of dimension at least 3, then the fundamental group of M actually determines completely determines the hyperbolic metric on M. Right? So the fact that you can read off the volume from the fundamental group, that just follows from Mostow formally. The fact that you can read it off in this form is something that is quite surprising. But I mean, just to reiterate how important this is, the thing is now, you see, if I take any three manifold, which is hyperbolic, then because the hyperbolic metric is unique, any invariant of the geometry is, in fact, a invariant of the topology, right? So if I take say, the figure 8 knot, and so I look at its exterior, which I realize is not actually quite a closed manifold of the kind I've been talking about, but I have difficulty drawing closed three manifolds, I apologize. So this is hyperbolic and of finite volume, and the volume turns out to be 2.02988 something, something, something. That number is in fact an invariant of, it's just an invariant of this knot. And one thing that, this will tie in a little to my talk tomorrow, that people work on now in three-dimensional topology is to better understand like what features of this correspond to this. I mean, by Perlman, you know that these geometric structures, they exist. And by Mostow, you know they're unique. But the exact way that topological features express themselves geometrically or conversely is not as well understood as one might like. So, OK, so I'd like to now explain, I'd like to convince you that this conjecture is true. And there's a couple ways I could go about doing this. And there are various theoretical reasons to believe this is true, but one of the reasons I really like working on three manifolds is you can do experiments. So I'm just going to show you data, pretty plots, which will convince you of that conjecture. And while the projector is warming up, let me just define something. So if I have a manifold n, let me define the torsion ratio just to be the thing we're taking the limit of. So log of so take the abunionization of the first homology, take the log, divide by the volume. Sorry? Oh, sorry, the torsion. Thank you. Take the torsion divided by the volume of the manifold. We just define this to be the torsion ratio of n. And then let me just multiply this by 6 pi so that the conjecture should now be that this thing goes to 1 as you take more and more covers. All right, so here is a plot. What is this a plot of? So this is from a paper of mine with Jeff Brock. So what we did is we started with 11 arithmetic hyperbolic well, they're not actually they're not manifolds, they're orbifolds. They come from the twist knots in S3. So you take a twist knot and you label the knot with some orbifold label, and that gives you typically a hyperbolic manifold. And there are a few of these, well, to be exact, 11, which are arithmetic. And so for each one of those guys, we went and we took a whole bunch of these congruence covers that are required by the conjecture. And I think there's about 15,000 covers in all. And for each one, you go out and you build the cover, and you just compute its homology and compute this ratio, and then you plot it on this plot. And so you can see as the volume increases, so you can't see it anymore, but the figure 8 knot had volume about 2. That's the smallest volume knot complement. So as the volume increases out towards 30,000, so each dot here represents one of these covers. So this dot here represents something of volume about 2,500, whose torsion ratio is about 1.26. And anyway, as you see, as you go out, bigger and bigger volumes, these dots do cluster down along the line at height 1 as proposed by the conjecture. All right, questions?
What are the colors?
Dan asks, what are the colors? Yes, thank you. So the colors have to do with the part of the homology we're not looking at, namely the free part. So here, red means that the first cohomology of the cover is non-zero, and blue means that the first cohomology is 0. So in this, whether you have any free part plays no role in this number, but that's so about 35% of the dots are red, and the rest are blue. Does anybody notice anything about the red versus blue dots? The red are lower, yeah. And so, in fact, let's just make a plot here to emphasize this. So in this case, what I did is I just looked at the manifolds whose volume was at least 15,000. So it's like the second half of the preceding plot. And then I made a histogram of their torsion ratio. So here's the histogram for the red ones, and here's the one for the blue ones. So you can see here that the histogram for the red guys is shifted down slightly relative to the blue. And in fact, what I'll talk about tomorrow will have to do with why this thing is shifted and can you control how much is shifted. OK, so that's the arithmetic context. That was where Bergeron and Venkatesh were originally formulating this. Let's look at the non-arithmetic manifolds. So, as I said, these come from starting with these twist knots and then looking at orbifold labels on them and so on. So in this same kind of topological family, some of these orbifolds are arithmetic and some of them are not. So let's look at some of the ones that are not. And again, we do the same thing, compute their torsion ratios. So this case is, I think we looked at about 20 of them. And so we have about 30,000 covers now. And so here's the picture. And so what you notice is there's a lot less red. Right? The first plot I said is about 35% red. This is only 2% red. This is just further evidence that Agol's theorem is very hard to prove. And moreover, for the blue guys, in fact, stuff is converging to the line 1. And in fact, it's converging faster. It's not maybe obvious from this plot, but it is true. It's converging faster. Except there are these few occasional outliers where you have things that are way off the line. Again, the reasons for this is something I'll talk about some tomorrow. This is just a little plot comparing the arithmetic versus non-arithmetic guys when the Betti number is 0. So the blue here, that's the non-arithmetic ones, whereas the green is the arithmetic ones. Of course, this is, again, lopped off at volume greater than 15,000. This is 1 up to like 1.08. So this is already very narrow, but the non-arithmetic guys are even more concentrated. Other questions? All right, in that case, I will put the projector away. Okay, so it seems like, in particular, what I wanted to convey with those pictures was there's a lot of evidence for the conjecture as stated, and there's a lot of evidence that you should be able to erase this arithmetic here, at least maybe by imposing some additional condition. So it seems safe based on the data to conjecture the following, that, let's just say, it can remove arithmetic from conjecture if we add that the covers here have no cohomology. The only troublesome ones in my plots were these guys. All right, so manifolds like this, saying their first cohomology is trivial, that says rationally anyway, their homology is the same as the 3-sphere. So I'll call manifolds like this rational homology.
In the first slide, so all of those were not complements, right?
No, they were all closed manifolds.
Oh, they get closed up.
So they were built from a knot by putting an orbifold label on the knot. So they initially started off with a hyperbolic metric, which was singular along the knot with some cone angle. And I mean, of course, we could easily just take a small finite cover and get rid of that cone angle. But no, these are not coming from knot. These are all closed. I want to stick. There are analogs of this conjecture for things with cusps. And I should say, especially in the work of Bergeron and Venkatesh, I mean, they were interested much more in things other than, or in addition to, the case of hyperbolic 3 manifolds. So they actually formulated conjecture about lattices in semi-simple Lie groups that says that in the same situation, then you have torsion growth, and maybe in at most one degree, which isn't always going to be 1. It'll depend. So in other words, like you could take like some SLNR mod SLNZ or something like this, and there's this whole picture carries through. But I'm a small-minded 3 manifolds person, so this is what you get. Okay, so this conjecture seems safe. Now, you might worry it's safe because it's vacuous, in the sense that can you build a tower of covers like this where the cohomology is all 0? And the answer is you can. Well, it's non-trivial to do so. So in particular, let me just mention, and before Egel's work, people were working on the virtual Hawking conjecture. The first hope was that basically any kind of tower of covers like this, you'd eventually find some cohomology. That turned out to be false. So in work with Frank Caligari, I showed, well, I mean, really, as I'll explain, combined with work of Boston and Ellenberg, about 10 years ago, we showed that there exist towers of these congruence covers of both arithmetic and non-arithmetic manifolds. Where all of the manifolds have no cohomology. So you can, in fact, of course, this is pretty plausible in the non-arithmetic case from the plot I had. There were so few guys, few red dots. Are there questions about the statement? All right, to give credit where it's due. So what Frank and I did is we produced an initial example which was arithmetic. And our proof actually used, as I said, the definition of arithmetic is things that a number theorist, of which Frank is one, care about. And so in particular, you can use the whole Langland's machine of automorphic forms to analyze the cohomology of arithmetic hyperbolic three manifolds. So this is the same machinery that was, for example, used to prove Fermat's last theorem. So in the end, we show these things have no cohomology by ruling out the existence of certain Galois representations. There's a little caveat, though, which is in our proof, we had to use the generalized Riemann hypothesis, which is unfortunately not a theorem. It didn't bother me particularly, but I understand that number theorists is very important. But fortunately, Nigel Boston and Jordan Ellenberg were able to analyze our example using the much lower tech machinery of pro-P groups and give a non-conditional proof. And then we were able to sort of generalize that to cover a bunch of examples, both arithmetic and non-arithmetic. So what I want to do in the last 10 minutes, 12 minutes, is talk about a more recent result with Jeff Brock, which puts a limit on the degree which you can relax some of these hypotheses. So there's a parallel. I mean, I've been focusing on the torsion. That's the conjecture I'm thinking about. But there's a parallel story of just a Betty number, just a cohomology. And in that context, results of this form are known and sort of known with very weak hypotheses. So let me try to fill that in, and then I'll explain why somehow the torsion is more subtle than just a Betty number. So just a quick definition. All right, so if I have a hyperbolic manifold, which I will draw on a cartoon a dimension down because limited artistic skills. If I have a hyperbolic manifold and I have a point, then, well, of course, on a small enough scale, take some ball of radius epsilon, the ball that you get is just it's isometric to the corresponding ball in hyperbolic space. And I guess in my picture that's probably true for, if I increase epsilon a little, and maybe a little more, but eventually if I make the radius get big enough, this ball comes around and bumps into itself. And so the injectivity radius of my hyperbolic manifold at P is just the largest ball you can get before it runs into itself. So this is the supremum over epsilon, so that different ways I could say this, the ball of radius epsilon about P, I'll put it this way, is isometric to a ball in H3. So put another way, it's the first scale on which you see any topology about that point. And often we'll be interested in, I mean, this is a function. It varies depending on what point you're at. Often one is interested in the point where it is smallest. So if I just write the injectivity radius of M, I mean the infimum over P of the injectivity radius of M. And there are other ways to think about this, maybe more palatable. So this is another way of saying this is half the length of the shortest closed geodesic. So in my picture, well, cartoon, looks like the shortest geodesic is going to be a loop like this. And points on that are the ones where the injectivity radius is minimized. So another way of stating this condition here, equivalent way, I guess I didn't give this a name. Maybe I should have. It's getting late in the talk, so maybe it's good that I introduce it now. Let's call that situation over there an exhaustive tower of covers. So this just means that their intersection is trivial, or geometrically, if you think about it, this is the same as saying the injectivity radius goes to infinity. Any loop, right? So the injectivity radius of M is the smallest scale on which you can see topology anywhere. So saying the injectivity radius goes to infinity is saying that you unwrap all of the topology at some point. And I mean, somehow morally, if you have an exhaustive tower of covers, right, it means that on any fixed scale, eventually you can't tell you're not in hyperbolic space. So you should think of this as some kind of like geometric convergence of your manifolds to the universal cover. And I want to introduce a slightly more complicated notion of geometric convergence, so I can then state our result. So let's say a sequence of hyperbolic three manifolds. And unlike the manifolds that I've called Mn so far, these are not necessarily covers of a fixed thing. This is just some list of three manifolds. We'll say that this converges to H3 in the sense of Benjamini-Schramm. If the following is true. So if for any fixed scale, if we look at the points of the manifold where the injectivity radius is less than r, so you should think of r as being really big. We don't require that this set be empty, but just that it have small proportion in the whole manifold. So if we look at this, divide by the volume, this limit is equal to 0. So an example, so this is a weaker condition than saying the injectivity radius of Mn goes to infinity. Right, so an exhaustive tower of covers is certainly an example of something that's Benjamini-Schramm converging. And if, like probably all of you, you're seeing this for the first time, I would recommend just thinking of that as the definition. But unlike, as I said, what we were talking about before, these manifolds, they're not connected to each other. They're not covers of a fixed thing. They're just in a list. And so despite that, it turns out that this seemingly very weak notion of geometric convergence is actually enough to force a certain kind of convergence of the topology of these manifolds. So in particular, following result of 7 people, so I hope they forgive me if I not write all their names. So it's a result of Albers, Bergeron, Berenger, Golander, Nikolov, Ramon, and Samet from a couple years ago, that says that if we have a sequence of hyperbolic three manifolds which Benjamini-Schramm converge to H3, then if we look at just the Betti number, look at the rank of this free abelian group. If we normalize this properly, it turns out, by dividing by the volume, it turns out that this always limits to 0 as n goes to infinity. Now, of course, 0 occurs a lot of different ways in mathematics, it's fair to say. And this particular 0 is the first L2 Betti number of hyperbolic 3 space. And this result is the culmination of a long series of study by many people, Luke especially, in the context of like covers of, not necessarily three manifolds, but like just covers of CW complexes. You take a big exhaustive tower of covers of CW complexes and you look at their Betti numbers, then if you normalize appropriately, then things converge to some kind of L2 invariant of the universal cover. That's a sort of well-known story. The remarkable thing about this is that these guys are no longer covers of the same thing. They're just there. So in the context of trying to figure out the correct generality for this conjecture, which itself can be, I'll say in a minute, well, maybe I'll say it now. 1/6 pi is also, it turns out, an L2 invariant. So it's the L2 torsion, whatever that means, of hyperbolic 3 space. This fits very naturally into the context of these kind of questions. And so you could ask if you had a sequence of manifolds converging to H3 like this, if that alone is enough to force this kind of torsion growth with this particular limit. And maybe for that we would want to require, say, that the first Betti number be 0. And it turns out that that's not true. So the last thing I wanted to state was a theorem I did with Jeff Brock a couple years ago, which is that there exist hyperbolic 3 manifolds which converge in this Benjamini-Schramm sense to H3, where you don't see this torsion growth. And the reason you don't see the torsion growth is there's no torsion at all. Where the first homology of these manifolds is just 0. So homologically, these are indistinguishable from S3, even though they're converging geometrically to H3. And so the sort of hidden story, which I'm not obviously going to tell today, is that, I mean, you can, as I alluded to, try to put this into the context of something like this. Here we're talking about homology. What's going on here is, is there's, you can think about this in terms of the Ray-Singer analytic torsion of these manifolds. So there's some kind of conjecture really about that converging. So what the gist of this as compared to this is somehow convergence of torsion is a more subtle thing than convergence of Betti number. So let me stop there. Thank you for your attention.
Any questions?
Dan.
Lately, I've been talking about this meetings I've heard about not monoliths.
Right.
He's talking about manifolds with boundary.
Yes, there's it's the same statement.
What does the boundary
So it doesn't. So I think the statement is actually the same. Yeah, I don't think it. I don't think it makes any difference.
With this, you don't expect that the towers are unique that give you this, right?
No, I mean this is a conjecture about for any. This is suppose you have such covers, then conclusion. So we don't actually know now. There's not a single example where this conjecture is proved, and there's not a single tower of covers for which this is known. Yeah, so this is a conjecture about, yeah, so suppose you have all these, then you have this torsion growth. So one result, which I didn't mention, but a result of Thang Lei, is that you do know that for any such tower of covers, the lim sup of this quantity is less than 1 over 6 pi. So you can't have, I mean, basic topological arguments, it's easy to see that you're not going to get faster in exponential growth. But what Thang proves is that, in fact, that growth rate could be no more than this. But we have no examples where it's known to be.
So in your work with Brock, is the injectivity radius actually going to infinity?
No, it's not. So yeah, so the question was, I mean, so these manifolds are not covers of a fixed thing. They don't actually have injectivity radius going to infinity everywhere. So it's possible that if you just require that, then you would always get this torsion growth. And I think it's actually a really interesting question whether or not you could build integral homology spheres like this with injectivity radius large everywhere. And I have no idea how to do that. Or even bounded away from 0, actually. So the injectivity radius of these manifolds is generically large, but the minimum injectivity radius might actually be going to 0.